Welcome everybody to the second day of the AACOMA Roadshow event. I will be the moderator of today, so we'll later introduce the agenda of today. But allow me to 1 minute give a small introduction on what makes the organization happen today and why are we here. Well, it's because European Union, together with another few funding agencies, they have put together a research program to boost the usage and the applications, the manufacturing methodologies of composite materials in the free border region of Limburg, Netherlands, Limburg, Belgium, and region of Aachen. The idea is to get to know the other competences across the border, because they can be very close by and have a very good competence, and bring together the industry. So in this AACOMA project, which is a funding of about a few million euros to this region on this topic, the AACOMA project, one of the objectives, of course, to explain you information and to train you. So the region around what I just explained, the three area corner of Netherlands, Belgium, and Germany, really become a hotspot for the applications of composite materials. The technological partners, which are part and which are also organizing these events, are Sirris, Flanders Make, University of Liège, Centexbel, AAMI, Fontis, and AMAC. So they all have their own unique competences on composites manufacturing, composite applications, composite materials. And today we are proud to present you the second day of the Roadshow event. Yesterday we had a first event where also Bernard and Maarten and Michael from different partners of the AACOMA project have made some introductions and some explanations on the impact of COVID. Today we have engineer Linde De Vriese of Sirris as a presenter, and she will present. So Linde has more than 10 years of experience in composite materials, and she's also team leader of the Composite Application Lab at the University of Leuven and University of Ghent. So a lot of experience, and I'm sure we will learn a whole lot on the first presentation of today on manufacturing technologies of composite materials. Secondly, Jeroen Van Kasteren of Flanders Make will give an kind of an overview and a kind of technological overview about the guidelines on how to successfully bond composites by usage of adhesives. Hope this will be very interesting, because we see this as a rather common way to join or assemble composite parts together with other materials or with other composite parts. And then finally, for today at 12 o'clock, we have an online match, which I believe will become very interesting. So allow me to quickly introduce and explain the concept. So I'm sure you will stick around until 12 o'clock or until 1 o'clock. During the online matchmaking event, we will first launch you a few questions, a small questionnaire. So you also get to know what kind of other companies and what kind of industries are represented during the online matchmaking event. After that small introduction, we will also introduce you all to a few poll questions specifically on the topic of composite materials or composite applications. This way, you will also get a little bit of a feedback on what's driving the market, what are the bottlenecks, and maybe we can even have a small discussion on these poll questions to see how can we, what challenges are out there, and what kind of solutions do we want to bring forward in the future of composite manufacturing. The full agenda is, as I mentioned, a 3-day agenda. On December the 9th, there will be a final event, which is a 1-hour training, again by Sirris, who has a lot of expertise as well on composite materials. Engineer Didier Garin will give a training on the basics of composites for non-specialists. Good. Very briefly for today, please mute your mic during the presentations. There will be an opportunity for Q&A to answer your questions at the end of each presentation. And if you have a presentation, just type it in the chat, and we will come back to that question at the end of the presentation. Good, that's it from my side. I would now like to introduce mevrouw Linde De Vriese for her presentation on the manufacturing technologies of composite materials.
Thank you, Manuel, for the kind introduction. I will share my screen. Okay, good morning. I was given the privilege to talk to you about manufacturing technology for composites, and I have around 20 minutes to do that. It's quite a challenge as you see what is going around in composites world. There are a lot of exciting things to talk about, but I will try to keep the 20 minutes so we have time for questions afterwards. It was scheduled to have 10 minutes for questions and answers at the end of the presentation. So feel free to ask questions. It's always nice to have some interaction afterwards. A brief word about Sirris. Sirris is the knowledge center for the technological industry. What we do is we identify collective challenges. We do knowledge building in R&D projects. And then we do knowledge transfer and sharing of our knowledge. More specifically for composites, we have quite some experience in designing composite structures, but also optimizing process technologies for different applications. That brings me to the next slide. So there are a lot of applications going around. This is very important to keep in our head because when we talk about manufacturing technologies, there are really a lot of applications and they all have their own manufacturing technology specifically for that application. So when we talk about composites, they are used in medical fields. Aerospace is a very well-known sector for composite materials. We have the blades of wind turbines that are made of composites. We have sport and leisure applications, bikes. Automotive industry is also a very known sector, but composites are also used in construction, bridges, for example, and one emerging application is also shipbuilding. And mostly composites are used because of their lightweight properties, but there are many more advantages why it is interesting to use composites. But I will not have the time to go into that today. Today we want to talk about how are these products made. And to explain that a little bit more, I just want to show composite just to make sure that we all are on the same page in terms of what a composite is. So this is a composite product. When we zoom in a bit, we have reinforcing fibers. In this case, it's a carbon fiber. It is held together with a stitch. And then when we zoom in even more, we see the carbon fiber again, which is held together with a stitching. This is just to keep the carbon fiber together. And make sure that they are very well aligned. So all the structural load is carried by the unidirectional carbon in this case. When you cut the composites and you look at the cross section, then you see all the fibers. These are circles because we are looking at cross sections. So you can see that the fiber bundles in several directions. So this is a fiber that is in 90 degrees on the screen. This is a fiber that is along the screen surface. So this is a zero direction fiber. But basically, when we talk about composites, we are talking about a blend of a polymer, which needs to be very much next to the fiber, and we don't want any porosity next to this fiber. And this is very important when we start talking about manufacturing. The quality of a composite is mainly driven by the amount of impregnation of the fiber. So by that I mean we don't want any porosity inside of these composites. We want a polymer to be very much around the fiber so that we can have a good load transfer between the fiber and the polymer and the other fibers in the end. So that is our goal, to manufacture very composites. How do we do that? I'm sorry, I only have one formula for today, but I think it's nice to add this one. It will help us understand a bit more what is important when manufacturing composites. But let me start here at the right side. So we have a matrix. This can be a thermoset or a thermoplastic composite, thermoplastic resin, sorry. And we combine that with reinforcement. And in this case, we have a carbon fiber. Our challenge today is to blend the fibers and the matrix together. This is called impregnation. So here you see a cross section of the composite. So you have here a fiber bundle, and we want the resin, which is before processing. Before processing, we have the two constituents which are separate. We want to blend them well. So that means that you have a resin here at this side, and you basically want to push this resin inside of your fiber bundle so that you don't have any porosity at the end of your process. So during the process, you still have porosity. As you can see, these are the black spots. We want to end up with a composite that is very well impregnated. Now, we want this process to go quite fastly. This is one of the drivers that we see in industry. We want to go faster and faster with these kind of processes. And Darcy's law is a formula that very well describes the velocity of this impregnation process. And then we see, looking at this formula, that it's quite simple. We have three factors that drive the speed of this impregnation. First one is the permeability of the porous medium or of our fiber bundle in our case. We can assume this is more or less constant, so I will not talk about this a lot. What is important is the pressure gradient. It's quite easy to understand. The more pressure you put on the resin, the more easily you will impregnate your fiber bundle. And then the other one, which is also a very important parameter, is the viscosity of your resin. You can imagine that if the resin is more fluid-like, it's easy to impregnate. If it's more viscous, so it's more like a honey kind of viscosity, it's much more difficult to impregnate. And that leads to two material classes that we can use to divide composite manufacturing technologies. On the one hand, we keep these two parameters low for a good speed of processing. And it sounds more easy, and it is also why this is the mainstream composites, and it's also the first composite technology that was used. It uses thermosets. This is a blend of two liquids constituents, and they react chemically in your mold. So this is it's a quite easy process, low viscosity, low pressure. When we look at what is happening today, we see more and more advanced composites where you have a high viscosity, high pressure. You also need a high temperature for these kind of processes. So it's good to keep this in mind as I go further. We have kinds of material classes within composites, thermosets, where we have very fluid resins. We have an initial very low viscosity. During processing, this viscosity will rise in order to get a rigid structure. But initially we need low, mostly low, but there are also processes with higher pressures. Curing needs time. That is one of the main drawbacks of thermosets. Once it's impregnated, you still need time for the chemical reaction to go forwards. But once the material is fixed, you cannot post-shape it, so that's a drawback. It's also relatively brittle, and the drawbacks lead to more interest in thermoplastic processing at the moment. It's more difficult to process, but the products in general, they have a very nice opportunities that a thermoset composite doesn't have. And then I mainly talk about fast processing. You can process this material very fastly if you have the right pressures. Of course, it's a bit more challenging, but you can go to fast processing. This is why thermoplastics are very much used in automotive industry today. You can also, after your part is made, you can weld it again. You can assemble parts quite easy. Technologies are emerging for that. And the material is typically tougher. This is also very interesting for many applications. Okay, but if we go to the mainstream, so I start from the start, and during my presentation, I will expand a bit more on what is being done today more and more. So I will go towards the trends in composites manufacturing. One of the first technology was hand layup. So this is liquid molding. You have the liquid resin that you put on the fibers, you roll it and you cure it. Very manual and labor intensive. The technologies that is used for boats, for example, is vacuum infusion, very similar, but you close the mold with a bag and you pull vacuum on one side, and on the other side the resin is used to impregnate the fibers. So these are dry fibers in the mold. You end up with very large structures, boats, wind turbine blades, etc. And then the more advanced liquid molding process is high pressure RTM or RTM, where you have a closed mold, so double-sided mold, where you inject the resin with quite a high pressure, and these are composites that are used for more high-end applications. For example, automotive industry. Then two other liquid molding processes are filament winding. Here you see a tank that was developed quite recently. It has a diameter of 15 meters. It has more than 2,000 cubic meters of content. So this is a huge structure. This is made with filament winding. So you wind the fiber, which is already impregnated through a resin bath. But of course, there are also smaller tanks that are made with this kind of process. A variant is pultrusion, where you pull a fiber through a resin bath and impregnate that to make profiles like this. A very nice emerging technology that we see is using these mainstream technologies that have been around for many years, but using thermoplastics. So you get all the advantages of a thermoplastic composite, but you can still use the mainstream technologies, like, for example, pultrusion. This is an example by CQFD composites. Basically, you start from monomers which are combined in a mold or in a die. And in that die, there is a chemical reaction making a thermoplastic composite. So afterwards, that means that you can form this thermoplastic again into, or you can weld it to another structure, for example, by applying heat to the thermoplastic composites. This technology is also used for boats, for example. This is also in situ polymerization, where you again start from monomers, you mix them together. Because it's still a monomer, it's very fluid, and you can impregnate a boat, you can impregnate a wind turbine blade, and this has some advantages over thermoset composites. Okay, so here I stop. This was about the mainstream composites. Now I want to go a step further to explain what is going on today in industry. We see that today there is most of the time not one process anymore, but the process is divided in two separate processes. So we have talked about impregnation at the beginning of the presentation. This is mainly done now separately from the forming of composite products. So that means that you not only have fibers and resins on the market, but you have a whole range of impregnated semi-finished products that can be used to make a formed product. And these semi-finished products, they also have different properties. The semi-finished products that has been around for a long time is the LFT pellets for injection molding. What has been around also for a number of years is consolidated sheets. So these are sheets with many times in two directions, fibers, which are woven into a new structure. And what is emerging more and more is the use of tapes and touwbricks. And I will come back to that later to see what kind of technologies are needed for that. So these are used to forming processes from high to low pressures. As you might know, in aerospace, these kind of semi-finished products have been around for a long time, actually. But these semi-finished products, prepregs we call them, needed to be used in an autoclave. And here you see a picture of an autoclave. It needs a lot of energy. You need a lot of pressure inside of these autoclaves. And therefore, we see a very important trend in manufacturing is out of autoclave technologies where you don't need these big autoclaves, but you can use other technologies, as I will explain in the next slides. So I will start from this kind of semi-finished product, and then we will go and look more and more at the technologies that exist for tapes and for touwbricks as well. But let's start with the flat sheets. This is what is used in automotive, for example. And I think if I click on this, you will not see my screen. So I have to, sorry, I will need to stop sharing for a minute, and I will share again so you can see the movie. Voila. Okay, so this process describes the press forming of thermoplastic composites. It's a two-step process. So first you do a preheating under infrared heating. Here you see the thermoplastic sheets, which is clamped. This is also a lab scale test, by the way. So this is with a very versatile clamping unit. There's a transportation to the press, and then a press is closed. And since the material is melted completely, it can form quite easily into the shape that we want. And cycle this kind of process are around 2 minutes, 1 minute. So it's quite a fast process. And then we demold. It is possible to make these kind of products net shape. You can see here in the video, this was not yet the case. So basically what we would need to do is to trim the product afterwards. Oops. Sorry. Okay, some examples of this kind of process is used by Boeing, for example, already. These kind of clips. And then the next emerging technology is using patches of UDs. So you actually make a patch where you spot weld UDs on top of each other. They are consolidated, and then you use the same kind of process as I have just shown you, press forming into all kinds of products. So this is an example from Cetim, Diefenbacher and Fiberforge also are very strong in this. In the next step, we can also overmold. So this even goes a step further, where you can Here you see an example where you can see the composites, which is overmolded with white thermoplastic. So this is an injection molding over your thermoplastic sheet that was used as a semi-finished product. You can also use a taupreg, which is overmolded. You can use the sheets that we saw in the previous slides that is overmolded. This is a very interesting technology at the moment. Going even one step further, you can not only spot weld, as we saw in the previous slide, where you just weld the tapes on top of each other at specific spots, but you can also use a continuous process, and that means that you very locally weld the tape on the previous stack, and you can do that for a flat structure, you can do that for wound structures. Here are some examples from commercial players at the moment to make this kind of tape laying, as we call that. This is fully out of autoclave. You don't need high pressures. It's because it's very local. You need a fairly small force that can be applied by a robot, and you can apply the high temperature through laser radiation, for example. So this is used for tanks, hydrogen tanks, for example, who can withstand a pressure of around 700 bars can be made in this kind of technology. And then going one step further, because if we come from here, this comes very close to 3D printing. And that is actually what is done in recent years very intensively. These are all companies that started around 2013 or later. So these are recent small companies that are exploring how to 3D print continuous fibers. This was the first one on the market, Markforged. But there are other examples. Stratasys, they don't use a continuous fiber, but they use a chopped fiber. This is a very interesting company. They use a thermoset resin, and they embed the fiber with this resin, and then they UV cure. And the interesting thing is that they also can include wires and all kinds of sensors. Arevo, they make bikes with 3D printed composites. So they use a taupreg, which is impregnated, and they make all kinds of geometries with that. Very nice example from Anisoprint. This is a part that was traditionally made in aluminum. They changed to a composite centric structure, and now they are redesigning that with topology optimization. So you only need your material, well, you only use your material where you actually need it in your parts. So this is very interesting technology. This is thermwood. This is at larger scale, I would say. So this is for making molds. This is the mold for a helicopter blade. Very interesting technology. I see that my time is almost over, so I will speed up a bit. One of the very important, of course, trends is automation. Nice example, where they have a fully automated pilot line for more than 1 million parts per year. We see a lot of interest in draping technologies, fully automated, cutting technologies, also fully automated. This is a demonstrator that we have done at Sirris, making omega stiffeners fully automated. And then, of course, we go in the direction of digital twin. On the one hand, simulating processes. More and more, this is done quite accurately. I started 7 years ago with working with Aniform and simulating fiber directions during the process. And we see that during the course of these years, simulation programs have improved very much, so you can predict fiber directions and thickness of composites. On the other hand, we have a lot of technologies emerging on quality control. It's really seeing where the fiber is in your products after manufacturing. There are several technologies available. One other emerging technology is incorporating sensors, fiber break sensors, capacitive sensor. This was a project that was done together with the University of Ghent, where we looked at the infusion strategy for RTM products, and with the fiber break ratings, you can very nicely see when there is a resin at a certain time, and you can also monitor the cure of your product very well. And then the last technology I wanted to talk about is recycling technologies. They are also emerging very much, and I just want to leave at least a bit space of for questions. In summary, what we see is that more and more technologies are being combined to hybrid technologies. We see multifunction materials, embedding of sector sensors inside of your composite parts. Recycling technologies are very much evolved in the last few years, and there's a lot of effort going on in that field. Working towards digital twin, so process simulation, in situ inspection of the quality of composite parts is also one of the trends. Going towards fully automated fabrication and tool-less manufacturing is possible with 3D printing, where we expect a lot of emerging technologies in the next few years. Okay, I will leave it at that. Thank you very much for your attention, and please ask me any questions if you have them.
Thank you, Linde. Was a very nice one. We have an echo at the moment. Good, we have one question from Luc. So you mentioned high pressure injection of the resin, Linde. What injection pumps do you have for this? Maybe a recommendation of a brand or a manufacturer for this?
So for RTM, we work with Wolfangel, but there are other suppliers available for this. It really depends also on the quality you want at the end of in your product. So you have RTM at low pressures and then high pressure RTM at higher pressures, but there are many suppliers that can provide this.
Okay. I can myself answer the question of Luc, the next one. Can we get the presentations afterwards? Maybe Linde, can you share your presentation afterwards?
Sure. Yes.
Good. No. So within the AACOMA consortium, we're also making a website where all the information, eventually also the recordings, will be centralized. So also for you in the future, if you want to share it to a colleague, if you want to look at the presentations, you can go to that spot as well to find all the information. Good. Maybe I also have a question myself about the presentation, Linde, before we move into the next speaker or we wait for another question. 3D printing of continuous fiber. That methodology, do you also impregnate with another material, or do you just remain, let's say, with one material with a fiber with no impregnation? Or what's the methodology?
There is a wide variety for that. So there are companies, for example, the Arevo, which I showed, the bike manufacturing, they start with a taupreg. So that means that you have a filament, very much like unreinforced 3D printing, which has the fibers inside. And they just melt the fiber on the product and they consolidate that. But then there are other extremes, like the example that I showed you with the sensors integrated. They really put their fiber through a resin bath, so they impregnate in line. So they start with a dry fiber, put a resin bath, and then impregnate like that. There are other technologies where they start with a taupreg that is a little bit impregnated, and they add a pure thermoplastic fiber to that. To impregnate it even a bit more before they start laying the 3D geometry.
Okay, very interesting, very impressive. Good. I see also no further questions in the chat. So then I assume we proceed to the next presentation of Jeroen Van Kasteren. So now we got the first great presentation of Linde on showing the different manufacturing technologies and the principles behind it. Jeroen will explain more about how to put the pieces together, how to look at the assembly, and what's the role and the guidelines of usage of adhesives. Jeroen, take it away.
Yes, thank you, Manuel. I will share my screen. I think it's working. Good morning. My name is Jeroen Van Kasteren and I'm working for Flanders Make as a researcher in the Joint Material Lab. I want to show you which path you can take to come to a successful adhesive bond in composite structures. It's a small intro and I hope I will be able to give you a complete overview. For joining composites, the most used method is adhesive bonding. This is chosen for its benefits against mechanical joints. The most important benefits are an even force distribution over a big surface, and this can lead to relative thin materials with a weight reduction as a result. And with adhesive bonding, you also don't have to damage your material. For instance, by drilling, you have to. With adhesives, you can also bond dissimilar materials. The typical example is metal to composite bonding in the automotive. And in the automotive, they also make advantage of the extra functions of adhesive bonds, like sealing or damping. But adhesive bonding has unfortunately also some downsides. They have its limitation on its surface temperature, and they are sensible to aging. Aging on influence of UV, of water, temperature, salt, and mechanical forces. Adhesive joining is a special process. This means you cannot check the critical requirements without this surface testing. So you need to have an extensive quality system with relative highly trained workforce. And you have to also take measurement on the safety since you're working with chemicals. To recycle bonded parts is also challenging, but it's also challenging for composites, but it doesn't make it easier. To make use of the benefits and to deal with the challenges, we have a predefined path to design your product and process will help to come to a reliable adhesive bond. I've defined 6 steps for setting up an adhesive bond, and I will go through these 6 steps very briefly. The first and obvious step is to make your design, as in choosing your substrates, the adhesive, and the design of the bond line. Most of the cases, the substrates are a given fact. They are made out of fibers. This can be a carbon, a glass, or a natural material. But in the end, you will bond on the matrix, as a thermoset or a thermoplastic. In general, a thermoset is easier to bond compared to thermoplastics, since thermoplastics have in general a lower surface energy, especially the polyprop is very difficult to bond. The opposite substrate can be the same type of composite, or it's typical a metal construction, or for instance glass like a windshield. And each type of composites and the combination of substrates results in different requirements and also a different kind of adhesive. For instance, for bonding a windshield to a composite body has complete other requirements compared to a composite car body to a metal structure. The windshield bonding need to be strong and flexible to absorb movements due expansion and dynamic loads. And the bonding to the metal structure needs to be very rigid for a better drive control. Then the adhesive selection. In the adhesive selection we have requirements for the design properties, with the bonding strengths, the allowed elongation and the temperature resistance is the most common selection criteria. But also for the process we have some criteria, and the most common are the viscosity, the pot life and the curing time and temperature. Curing temperature are typical criteria for selecting a suitable adhesive. For structural bonding, epoxy is the most used adhesive. It has high strength on various materials, is good temperature resistant and has good properties against aging. But when you can't guarantee an even and very thin bond line, epoxy loses quite some strength, and metal acrylic and MMA adhesive may be the better choice. For non-structural adhesives, sealant types as an MS polymer or one component polyurethane can be chosen with their excellent sealing and damping properties. Maybe you can also think about a PSA, a pressure sensitive adhesive, or just a tape. A very quick adhesion on smooth surfaces. This can be very interesting. As I told you, composite with thermoplastic matrix, especially the polyprop, have a very low surface energy and challenging to bond. But making use of a fleece can be a solution for this. This fleece is part of the composite layer, of the top layer of the composite, and the adhesive will be mechanical anchored into the fleece as the bonding force. Simultaneously with the adhesive selection, you have to design the bond line. Please design the bond line to absorb tensile, compression or shear forces and avoid peel forces. These peel forces causes a very high peak forces, and this joint cannot withstand them. And in a good design, you prevent exposure on the bond to UV or ingress of water and chemicals. Preventing this will lower the influence of aging and thus enlarge the lifetime. The design of the bond line depends on the type of substrates, adhesives and the type of application. A thin bond line is used for rigid structural joints, and a thicker bond line can absorb movements and can also absorb tolerances in the substrates, in the composites. When the materials and the geometry are defined, testing the adhesive bond is highly recommended. Testing can be done on coupon samples or on real models. The testing is normally done in combination of accelerated aging cycles to test the durability. And which cycles you choose, that's depending on the outcome of a risk analysis. Testing can be done in typical 1 week or maybe up to 5,000 hours. After finalizing your design, the next step is how to process your bonding. What is the optimum method to prepare the bonding surface? How can the adhesives be prepared and applied? And how to ensure the correct bond line thickness? For your treatment of the substrates, a proper treatment of the substrate is often underestimated. I dare to state that more than 80% of the bonding failures, a wrong surface treatment is the root cause. In many cases, the finger is pointed to the adhesive supplier, but the quality of the adhesive itself is rarely the root cause. But whatever the treatment will be, the first step is cleaning, and the chosen cleaning solvent needs to be able to remove all contaminations but not damage your material. Release agents are often present at composites, and they can be very difficult to remove. And even silicon products are still used as release agents, and it's visually impossible to remove or cover all silicons. You really have to state that these materials are forbidden in your production or at your supplier. By cleaning, thermoplastics are more sensitive to solvents compared to thermoset materials. The cleaning agent of the solvent can create stress cracks or dissolve the material. And so your cleaning agents has to be selected for this. And after cleaning, in most cases, you will need to activate the surface. I'll go through some examples. One of them is abrading the surface with the goal to remove all contaminations and moisture in the top layer. And for composites, extra care is needed. Due to the hygroscopic properties of the fibers, you have to prevent that the fibers are exposed on the surface. The fibers will attract water or solvent, which can become between the adhesive and the substrates. Another method is a plasma treatment. This is a clean and fast method to treat a bonding surface. This plasma treatment can clean, coat, and activate surfaces. For composites and for plastics, it's most used for activating the surface. The plasma treated surface results in a higher surface energy and more reactive groups. And it has the biggest effect on thermoplastic composites. The benefit of plasma unit is also that you easily can integrate it in a production line. The plasma unit can be placed on a robot or cobot for treating the exact correct area with a constant speed, power and distance. The primers are also widely used. Primers create a link between the adhesion from the substrate to the primer and from the primer to the adhesive. But be aware that a primer can become the weakest link when not properly used. Example, when not wait for long enough that the solvent is evaporated, or when to use a too thick bond primer layer. And always choose your primer with together with adhesive. The primer is designed for a specific adhesive. At last, a surface treatment unique for a composite is to make use of a so-called peel ply. With a peel ply, the last top fiber layer is embedded in the matrix, and this layer can be teared off just before bonding. This creates directly a fresh and clean bonding surface, and further treatment may be necessary afterwards, but you start with no contamination from the outside. Once the surface treatment is defined, you have to define a method to do the bonding itself, and a complete process has to be defined. The correct method of mixing, how much adhesive you will prepare at once, applying the adhesive, how to cover the complete bonding area with no air entrapments, and how to join and what tools are needed. And in the end, within the work life or pot life, how to fixate, and maybe possibilities to speed up curing by adding heat. For the last step, a big remark: do not move the substrates after fixation. A common mistake is to just reposition the parts a bit after the pot life, and this will lead to a very weak bond. With defining the method, the way of working has to be clearly defined in a work instruction, including the critical parameters such as a minimum and maximum time for the next step after cleaning or priming, your pot life or temperature and humidity boundaries. And simultaneously to defining the methods for applying adhesive, the creative automation can be defined. Each step can be automated on different levels, from simple tools for mixing to fully automated and controlled meter and mixing system. This can also be extended with automated applying and fixation. The benefits of automated production are not only the cost and the shortened production times, but also the constant quality and also eliminate the exposure to hazardous materials are even important benefits. But in the end, the grade of automation is mainly dependent on size and quantities of the assembly. When you have defined your method, extra attention has to be paid to the quality assurance. What I've explained, that adhesive bonding is a special process where you can't judge the critical quality requirements without destructive testing, so you have to build your quality in your process. Important items to be defined are what data needs to be recorded. All the relevant data which can affect the joint is recorded. This data such as the room temperature and humidity, the batch of the used adhesive and primers, the different timings of a begin, the end of a process step. And normally each bonded part must be traceable to this data. So each bonded part has its batch or serial number for tracing. And about this batch size, it's part of your risk analysis what you define as a batch. It's possible to define a batch size the bonded parts of a month of production. But when you have a non-conformity reported in the field, this complete batch has to be isolated and inspected. And for instance, when you define a single product as a batch, you will have more administration and more testing during production, but in case of a non-conformity, you might be able to prove that other batches don't have this issue without further testing. Besides logging the data, inspections and non-destructive testing can be done for the quality control. There are some straightforward testings without much investment and more complex methods. Some methods are just visual check of squeezed out adhesive. This can be a proof that the complete bonding area is filled, or just knock on the bonded area and recognize air entrapments or debonding. Boeing has defined its own Boeing tapping hammer for it. It's their standardized tool. Another thing is just let a part of adhesive cure during your production batch. Afterwards, you can measure the hardness, and this is also a straightforward method to check the quality of your adhesive. Testing on air or water tightness can also be done if applicable to your design. Other common methods is analysis with a scanner. This is done in a wide range of frequencies or with an heat flow. An example is the Fokker bonder and the Fokker bond test. But all these tests, you have to have a lot of experience, and in the end, it didn't give you an answer on the adhesion strength of or the quality of the bond. So we can also do some destructive testing. We can produce a side sample parallel to the serial production. This makes you able to do destructive testing, and the sample is preferable made out of the same substrate material as your product. This will give you some more insights on the quality of the bond. Other quality aspects to be defined are who's able and who's responsible for which tasks. To work in a controlled environment is maybe an obvious step, but it's nevertheless an important one. Ensure that the environment throughout your process is monitored and without the working condition as defined in the different processes. And this is including the transport and storage of your adhesives, but also the operating conditions in means of temperature and humidity. And take attention on contamination control and safety regulations regarding health and environment. All these discussed steps can be taken really well, but in the end, the quality is made by the workforce. Therefore, you have to train your staff and operators. There are mainly 3 levels of knowledge bases. You have the adhesive engineer. He is responsible for the high-risk bonds, economically or safety-wise. And he will also do the design and define the process in detail. You have the adhesive specialist. He's able to take corrective actions on the shop floor and do the quality control. And then you have the adhesive bonder. He has a wide knowledge about adhesive bonding for performing constant quality. There are different market-specific courses available, but in Europe, an industry standard is set up for adhesive bonding. These European diplomas are now worldwide recognized, and this content is assured by the European Welding Federation. These courses are held across Europe, in Belgium at Flanders Make, in Germany, the Netherlands, and in many other countries, even outside Europe. To standardize your adhesive bonding activities, 2 German standards are introduced the last 15 years. Both of these standards can be seen as an extension of the ISO 9001 quality standard. The DIN 6701 was the first standard, and it is especially developed for the rail industry. This standard was the base for the DIN 2304, which is applicable for the industry in general. And these standards are a really good tool to help you to control your bonding activities. I'm coming to the end of my presentation. I hope I've given you a small insight in steps and points of attention to come to an adhesive joint in composite structures. So if there are any questions, please ask them, and thank you.
Thank you, Jeroen, for the presentation. My main takeaways, what I remember, was that the importance of surface treatment and process control are very important. So I learned a lot. Again, thank you.